Australia, smart plane, route cruise 10,000. Cruise bin Mike, initial altitude at 2,000, visual, clear for takeoff.
The first real demonstration that man was able to alter the course of the weather came a little over 20 years ago. In 1946, two scientists in the United States discovered that by dropping pieces of dry ice from an aircraft into a cloud, they produced a snowstorm. The idea was immediately taken up in Australia by the CSIRO Division of Radiophysics, and experiments were soon underway to find out whether extra rain could be stimulated by this method. The trials took place on days when there were a number of separate but similar clouds in the same general area. A check was first made by radar to see whether any of the clouds already contained raindrops. If there were no raindrops present, then a hundredweight or two of dry ice was tipped into the top of one of them. These experiments were successful. When conditions were suitable, most of the clouds which had been treated with dry ice rained soon afterwards, while the other clouds around did not. But it was soon realized that this would not be an economical method of making rain over a large area. It would mean that many tons of dry ice would have to be taken to high altitudes above the cloud tops.
It was an American scientist, Bernie Vonnegut, who first suggested that silver iodide be used instead of dry ice, and perhaps much less of it would be needed. To understand how silver iodide can induce a cloud to rain, it's first of all necessary to know something of the nature of clouds themselves. The sort of cloud that we're interested in is formed in the first place by air rising up and the moisture cooling and condensing in the form of minute water droplets. If we could take a microscope and have a look at a portion of this cloud, we would find that these droplets are so tiny that it requires about 1 million of them to form one raindrop. They're so light that they appear to float in the air, going up and down with the air currents. The temperatures in these clouds are frequently below freezing, but the droplets are still in the form of liquid water. How then can a raindrop, which requires 1 million or more of these tiny droplets, be formed? One way involves the formation of ice crystals. If an ice crystal forms in a cloud which is below freezing point, it grows rapidly at the expense of the surrounding water droplets and becomes a snowflake. The snowflake grows as it falls through the cloud. Pieces may splinter off, and these grow into new snowflakes. In most parts of Australia, these snowflakes melt as they fall through the air at lower levels, and rain is produced. Now, these ice crystals form in the first place in the presence of ice nuclei, minute particles which have the special property of starting the freezing process. Sometimes there are enough of these nuclei present and the clouds rain of their own accord. If there are not enough natural nuclei present in the atmosphere, it is possible to seed the clouds with artificial nuclei. So far, silver iodide crystals have proved to be the most effective and convenient artificial ice nuclei. If we burn a solution of silver iodide, enormous numbers of minute crystals are formed. These are so small that they form an invisible smoke. The crystals are similar in structure to ice crystals and act as ice nuclei, providing an excellent trigger for the rainmaking process. In a real cloud, the ice crystals would continue to grow as they fell through the cloud until they melt and become rain.
Some of the first trials with silver iodide were made with burners placed on the ground, the idea being that the smoke would be carried upwards by air currents to the cloud level. This method was unsuccessful because the smoke rose only very slowly, and if it ever reached the levels of supercooled clouds, it had by that time lost most of its ice nucleating properties due to exposure to sunlight. This difficulty was overcome by generating the silver iodide nuclei with burners fitted to the wings of an aircraft. In this way, the ice nucleating crystals were carried right into the clouds before they had time to decay. The seeding solution was pumped to the burners on the wings, where it was ignited by a spark plug.
These trials gave much the same results as with dry ice. When conditions were suitable, the seeded clouds gave several times more rain than the unseeded clouds. But much less silver iodide was needed, and it was not necessary to climb above the cloud. With cumulus clouds, which are formed in rising currents of air, the smoke can be released at the base in the up currents and is soon distributed throughout the rest of the cloud. And if the temperature at the top of the cloud is cooler than -10 degrees centigrade, then rain usually falls about 20 minutes later. With stratiform cloud, however, the updrafts are not nearly so intense. If the smoke were released at the base, it would take very much longer for it to be distributed throughout the cloud. So, seeding is done directly at the -10 degree centigrade level, and the rain usually falls from half an hour to 3/4 of an hour later. For successful seeding, for both types of cloud, the depth of the cloud should be at least half the distance from the ground to the base of the cloud. Otherwise, if rain were stimulated, it would tend to evaporate in the drier air underneath the cloud.
Rain-making trials with silver iodide were first carried out over large areas in the 1950s. Specific regions were chosen in various parts of Australia where the rainfall over a seeded area was compared with that over an unseeded area. These trials showed that rainfall can indeed be increased in areas where the climate is suitable, such as on the inland western slopes. And during the course of the experiments, more was learnt about the physics of clouds. But several new questions arose. For instance, there was strong evidence that the effects of seeding tend to persist even after the seeding has ended.
It seems most unlikely that silver iodide smoke will remain in the seeded area for more than a few hours or days at the most. And yet the increased rainfall following seeding tends to persist for weeks or even months. We don't yet fully understand this unexpected result, and the causes of it are still being investigated. However, there is an old saying that rain begets rain and drought begets drought. This is borne out by the records, where it is seen that rainfall patterns tend to persist for a long while. So it is possible that increases due to seeding may persist by a similar mechanism. In order to investigate these effects more fully, a new large-scale experiment was started in Tasmania in 1964. A target area was selected in the Central Plateau region. This was of particular interest as it forms the main catchment of a large hydroelectric scheme. Extra rain here would be of great value, as it would add to the water available for generating power. Clouds in the target area are seeded or not seeded on a random basis, and the rainfall in the target area is compared with that in the two control areas on either side of the central target area. These control areas are never seeded. The comparison of the area rainfalls will then show whether the rainfall in the target area has been increased or not. This whole operation is carried out in alternate years, but the rainfall measurements are made in all years. So persistent effects of seeding can be investigated as they rise and fall away following the start and the end of seeding.
The Tasmanian experiments are being conducted by CSIRO in collaboration with the Hydroelectric Commission. During a seeded year, the cloud seeding officer in Hobart gets regular forecasts from the Weather Bureau. A specially fitted aircraft is used, and there are 2 crews, each consisting of a pilot and a cloud seeding officer, who also acts as the navigator. If the right supercooled cloud systems are approaching the target area, the decision is made for the duty crew to fly. During the climb, the cloud seeding officer plots the temperature at various levels and measures the depth of the cloud. Once he knows the direction of the wind and its speed, he can calculate where the silver iodide should be released so that the rain will fall within the target area. The silver iodide solution is pumped to the burners on each wing and ignited. Rain gauges are placed at regular intervals throughout the target and control areas. This rain gauge at Bronte Park is in the target area. Like the others, it is read every morning at 9 o'clock. All daily readings are sent to the Bureau of Meteorology. Since no one at the Bureau knows when the target area was seeded, there's no chance of bias in working out the total rainfall in each area for any particular period. The Tasmanian trials are still going on. When they're complete, it will be possible to calculate how much extra rain was caused by seeding. In the meantime, the results of 20 years' research in scientific cloud seeding are now being passed on to state governments for use all over Australia.
It's now clear that there are many parts of Australia where clouds suitable for seeding occur reasonably often. And it's quite clear that the right methods of seeding can induce them to increase the rainfall. In this course, we aim to give you 3 things. First, comprehensive account of the background of cloud seeding and its physical basis. Second, a description of the methods that we use. And third, how you can apply them in various parts of Australia.
New South Wales, Victoria, South Australia, Western Australia and Queensland all conduct cloud seeding operations. It's often a collaborative affair between several government departments.
Meteorology.
Could I have the cloud seeding forecast for the Waterworks catchment area, please?
Oh yes, Con. The southerly stream this morning is quite cold and unstable. Suitable cumulus cloud today.
4/8. Base 2 to 3,000 feet. Tops 10 and some as high as 15.
The winds at 5,000 feet southwesterly at 30, at 10 southwesterly 40, and at 15,000 feet west-southwest 60. The freezing level 7,000 feet, -5, 10,000, -8, 11, and -10, 12,000 feet.
Specially fitted light aircraft can be ready at short notice whenever conditions appear suitable. The target may be a water catchment, a wheat crop, undergrowth on a forest floor. The procedure is the same. The clouds are seeded upwind from the target so that by the time the rain starts, it will fall where it is needed. Exactly how much the rainfall can be increased is still the subject of critical assessment. In places where suitable cloud systems don't occur, even the best cloud seeding methods cannot produce rain. It's in the areas of light to medium rainfall that the best prospects for rainmaking lie. In the wheatlands of the Mallee, a half-inch increase in the rainfall seems quite possible. Falling during the growing season, this could add something like $2 million to the value of the wheat crop, a worthwhile return certainly for an investment of several $1,000s. And there's no doubt about the value of additional rain for generating hydroelectric power and for damping down forest areas to reduce the hazard of bushfires. What we already know about cloud seeding is being actively applied, but new techniques need to be developed. For example, for treating types of clouds which don't react to silver iodide. And so the research is still going on. We need to know much more about the natural behavior of clouds and to understand more fully the basic physics of clouds and rain. Such fundamental research will always be an essential part of any successful method of rainmaking.